For some problems, supercomputers aren't that super. Quantum computing and drug discovery. Drug design and discovery are complex, time-consuming processes. Think years and more often than not, decades. They start with the identification of a biological target, a protein or receptor believed to be involved in a specific disease. Small molecules that have the potential to interact with the target are then identified and evaluated for safety and efficacy before being optimized to improve their effectiveness and reduce their side effects. This is before they can finally be tested in preclinical and clinical trials. In today's world, drug design frequently relies on computational techniques that help simulate the behavior of a molecule and its interaction with a target. While physicists and chemists routinely use computers to simulate the behavior of atoms and molecules, such simulations require massive amounts of computing power because interactions between three or more particles quickly become tremendously complex. This complexity is compounded by the fact that electrons obey the laws of quantum mechanics, which allow for strange phenomena like superposition, i.e., the ability of a quantum system to exist in multiple states simultaneously. A single quantum particle, such as an electron for instance, can mind-bogglingly exist in multiple locations at the same time. Quantum systems can also become entangled, which means that the state of one cog in the system is dependent on the state of all the others, even when they're separated by large distances. They also exhibit quantum fluctuations caused by the Heisenberg uncertainty principle that makes it difficult to predict the behavior of a quantum system, even when its initial state is known. The state of quantum systems, thus, cannot be described by a single set of classical variables like position and momentum. They must instead be described by a wave function that contains information about all possible states of the system. Classical computers that obey the laws of Newtonian physics perform abysmally when confronted with the simulation of quantum phenomena. Pharmaceutical molecules typically contain 50 to 80 atoms, while the proteins that the drugs interact with tend to contain thousands. Modern supercomputers may have impressive processing power, but they lack the complexity needed to identify intricate patterns in large datasets. This is especially true when examining proteins and their possible folding structures, an issue of great importance for biology and medicine, given that protein shape defines its function. Uncovering how a single chain of 100 amino acids folds is no easy feat, as it has trillions of potential configurations and requires more than just the brute force typically leveraged to simulate protein folding, since no computer has the necessary working memory to handle the trillions of possible combinations of individual folds. This is where quantum computers come in. Quantum computers are fundamentally different beasts that can perform complex computations exponentially faster and with only a fraction of the overall energy required by classical computers, and could therefore significantly expedite the drug discovery and development process. Quantum computers, however, go beyond just being able to speed up the rate at which classical computers perform calculations, and also have the potential to open up completely new avenues for research in the domain in which they're being deployed. In the case of our running drug development example, for instance, they could also be used to simulate the behavior of enzymes that are crucial in the metabolism of drugs and help identify new drugs that are metabolized more quickly or slowly than existing ones to help reduce side effects and improve efficacy. They could also be used to optimize the structure of drug candidates by simulating the behavior of different conformations of a molecule, thus helping to identify new drugs that are more stable and have better pharmacokinetic properties than existing ones. Quantum algorithms are revolutionizing how complex problems and puzzles such as protein folding can be solved. They create multidimensional spaces to find patterns that link data points together. In this case of protein folding, these patterns tell us the minimum energy configuration of the molecule, which also happens to be the solution to the problem. Classical computers just can't match up. They simply cannot do what quantum hardware paired with advanced algorithms can. As quantum hardware scales and quantum algorithms advance, they could tackle protein folding problems and many others that are far too complex for any supercomputer. Quantum computing and climate change. Drug design and discovery was an example of one application that quantum computers have the potential to revolutionize, but it certainly is not the only one. They can help us solve many other problems as well, including one of the most pressing problems of our time, climate change. At present, The impact of global warming is forecasted through the use of computer models that simulate the Earth's climate. These models take into account factors such as greenhouse gas emissions, changes in land use, and the behavior of oceans and the atmosphere, and use complex mathematical equations to simulate the interactions between these factors and provide projections of future climate conditions. Quantum computers have the potential to not only expedite the creation of climate simulations, but also to make them more accurate and efficient because, as we've already noted, when coupled with the right algorithms, quantum computers can process large amounts of data faster and more accurately than classical computers. They can, for instance, be used to simulate the behavior of the Earth's oceans. Ocean circulation plays a crucial role in regulating the Earth's climate, and quantum computers can simulate the behavior of ocean currents to predict how currents, sea level, ocean temperature, and acidity will change in future. Quantum computers can also be used to simulate the behavior of the Earth's atmosphere by analyzing large amounts of data from weather stations and satellites to accurately predict future changes to temperature and precipitation patterns. Lastly, only for the purpose of this video, quantum computers can also be used to optimize the parameters of existing climate models to pull us out of any delusions we might still have about climate change and its long-term effects. Rounding up, these are just two of several quantum computing applications that show that quantum computing definitely has its place. Which brings us to our next question. How do quantum computers really work, and what sets them apart from all the classical devices that we're used to using? Subscribe to stay tuned as I dive deeper into topics related to quantum